Neurophysiology, not an easy subject. Action potentials move, but even the best text can only present static figures. That is why we have made the interactive learning tool Neurons in Action, allowing you to learn by simulating experiments on your computer. In the simplest tutorial, you deliver a current pulse to charge the capacitance of a plain lipid bilayer. Then you add membrane components one by one and deliver the pulse each time. Of course, you can change any of the membrane parameters and rerun any of the simulations. As the tutorials become more complex, you discover the heart of Neurons in Action, its moving graphs. Here, for example, is the unmyelinated squid axon, impaled with 4 color-coded recording electrodes and a stimulating electrode at its left end. As you observe the action potential moving along the axon, you also record it as a function of time at each colored electrode. And now you do experiments by calling up the parameters menu and changing a parameter, such as decreasing the diameter here by 10 times. Then you rerun the simulation. In this tutorial, you can also change the length, the capacitance, the channel densities, ENA or EK, the temperature, or the position of the stimulating electrode. Other tutorials offer additional experimental possibilities. In the myelinated axon tutorial, for example, you can change the number of myelin wraps, or the parameters of the myelinated regions or of the nodes. At the most complex level, you can simulate a motor neuron with 3 synaptic inputs to its dendrites. You control each input, its conductance, its timing, the location of each synapse on the dendrite, and whether the synapse is excitatory or inhibitory. You then observe where the action potential initiates and how the voltage spreads within the cell. The partial demyelination tutorial is especially relevant for medical students. Here, the left half of a myelinated axon is demyelinated, an abnormal condition simulating multiple sclerosis. When the axon is stimulated at its left end, the action potential travels slowly in the bare axon, then takes off when it hits the myelinated region. But watch what happens when an impulse traveling in the myelinated portion suddenly hits the demyelinated region. Now, experiment with the bare axon parameters to see what can cause the impulse to invade the demyelinated region. Here, we decrease the potassium channel density to half, then rerun the simulation. If you understand impulse propagation, you will be able to make other changes in the parameters of the bare axon, or of the myelinated segments, or even of the temperature that will keep the impulse from failing. When you are puzzled about a result in any of the tutorials, you can follow hyperlinks to explanations or more information. With Neurons in Action, you learn neurophysiology as you observe action potentials and synaptic potentials, their underlying currents and conductances under different experimental conditions. The hyperlinks lead you ultimately to PDFs of classic papers, including the papers of the giants whose equations made these simulations possible.